Bismillahirrahmanirrahim. Dear students, we are talking about the first year class and lecture number 29, and we are continuing the molecular orbital theory. And in the previous lecture I explained the structure of nitrogen, and now we have three more: boron, oxygen and fluorine. Molecular orbital theory. And in the previous lecture I explained the structure and how molecule of nitrogen is going to be formed and give the diamagnetic behavior. Dear students, this is the boron and atomic number is 5. Atomic number is 5, boron. 1s2, 2s2, 2px1. There is only one electron here. I am mentioning many times that you can draw also for the 1s2 just like for the helium. But it is to be complete because it is complete. K shell and K shell for the 1s2 is complete. That's the no need for drawing. But we can draw also. It can participate. Then 2s2 as we done for the helium, same. You can draw also. But here only we draw one electron which is in the 2px. So if you see the relative energies, in the relative energies of molecular orbitals, there are 2 points A and B. For the A point, for the oxygen and fluorine, you have to fill first sigma 2px, then pi 2py and pi 2pz. But in the B part, you can see for the hydrogen, helium, boron, carbon and nitrogen. So first you have to fill pi 2py, pi 2pz, then 2px raised. I explained the whole topic. Let's send this one. So that is why boron atom number 5, only one electron present at 2px in the first atomic orbital. In other boron atom number 5, and there is only one electron here in the 2px. So when they are going to be mixed to give a 2 molecular orbitals, one is called bonding, another is called anti-bonding. So in the bonding molecular orbital, one electron is here, one is here. So one electron will be shifted in the pi 2py and another is going to be 2pz. This is according to the Hund's rule. If 2 degenerated atomic orbitals are available and you want to fill more than 2 electrons, then separately by the same spin you have to fill. Don't fill 2 electrons directly in the 2py. So 1 electron in 2py and 1 electron in 2pz. 2 electrons and 2 are filled. Sigma 2px in bonding molecular orbital empty. Pi star 2py, pi star 2pz empty, and sigma star 2px is also empty. So this is the energy diagram of boron molecule. In the book, this drawing is not available. In this book, drawing is not available. So that's why you must draw it in your copy, and the small page you have to put in your book also. Because when in examination this asks, you must draw it. If you don't draw, then you will lose your marks. Without drawing, without this energy diagram, you can't explain the electronic configuration, you can't give the paramagnetic behavior, you can't give the bond order also. That's why this is very important. This is the normal electronic configuration: 1s2, 2s2, 2px1, 5 atomic number. And if the boron molecule is going to form, 1s2 is complete, sigma 1s2 and sigma star 1s2 are put in the K and K shell 2 electrons each. sigma 2 has 2 electrons, sigma star 2 has 2 electrons. Total you have to find 10 electrons, so they are going to be filled. 8 are going to be filled. 2 and 2, 4, 4 and 4, 8. Finished. Only 2 electrons remain. So one will be either in the pi 2py and another will be either in the pi 2pz. So if the 2 electrons are in unpaired, with the same spin, 1, 1 each. So if the 2 electrons are unpaired, you learn the paramagnetic properties of molecules. So boron is of paramagnetic nature. It has a paramagnetic behavior and 270 kilojoules per mole amount of energy is required to break. So in the vapor phase, boron forms molecule and shows paramagnetic nature, and 270 kilojoules per mole amount of energy is going to be required to break this bond. Bond order, yes, confirm. 2 electrons, C1 and 1, 2, no other, 2, 0 divided by 2 you will get 1. So one bond can be formed in the boron molecule. So this is, student, how the boron molecule is going to be formed, and draw it very accurately, and then you have to put in your book. Very important, this one. Now again another molecule which is going to paramagnetic nature I am going to explain, for the oxygen. This is for the boron. Oxygen. How oxygen molecule is formed according to molecular orbital theory. Molecular orbital theory. Usually oxygen is atomic number 8. 1s2, 2s2, 2px, 2py, 2pz. So 4, 3, 7, like this. So there are 4 electrons present in the P. 4 electrons there are. So we will write these 4. So these 2 oxygen atoms combine to the oxygen molecule. 1s2, 2s2 and 2p4. This is the electronic configuration. Then I am going to draw the energy diagram, and same principle I use for the boron, that you have to fill first oxygen first you have to fill sigma 2px, then pi 2py and pi 2pz. If you see, visit the relative energy of the atomic orbitals. So first you have to fill sigma 2px. This is the energy. And this one is oxygen. Atomic number 8. And there are 4 electrons. P like this. Atomic orbital. Again 2p. Oxygen atomic number is 8. So there are 2 atomic orbitals. Mixed together 2 molecular orbitals, one is bonding and another is anti-bonding. So as per rules, that you have to fill up with the two electrons here in sigma 2px. Sigma 2px. Two electrons sigma 2px. This is the bonding molecular orbital. Total 4 and 4, 8. There are 8 electrons are here. To fill the sigma 2px according to the rule we have in the relative energies of the bonding orbitals. Then you have to fill pi 2py and pi 2pz. So one electron, second electron, one and one, two electrons are there again. So students, there are 6 now. 6 electrons. Pi 2py 2 electrons and pi 2pz 2 electrons. If you see the energy, and in your book 2s2 is also drawn. It's your choice. If you draw, it's okay. If not drawn, it's your choice. Because the nitrogen is not drawn, the fluorine is not drawn, in the boron I told you no need for this. But if you draw, it's okay. So dear students, sigma 2px 2 electrons and pi 2py and pi 2pz again 2 electrons, 6 electrons are going to be outside. Now, this is pi star 2py and pi star 2pz. If the two degenerated atomic orbitals are available and you want to accommodate more than 1 electrons, the same rule is that according to Hund's rule, 1 each. Same I told you in the boron. So you have to put 1 each in the pi star 2py and pi 2pz in the unpaired form. And this is a sigma star 2px anti-bonding molecular orbital. So 2, 4, 2 to 4, total 8, 2, 4, 6 and 2, 8. This is the electronic configuration and this is the whole energy level diagram of the oxygen molecule. According to this electronic configuration, we have to go proceed now. For the 1s2, already I told you K shell and K shell, they are going to be filled. Then sigma 2s2, then sigma star 2s2, then sigma 2px2, then pi 2py2, then is equal to pi 2pz2, the last pi star 2py is equal to pi star 2pz. So in the pi star 2py there is 1 electron, in the pi star 2pz there is also 1 electron. You write in bold that you can understand that these 2 electrons are unpaired. So the oxygen molecule in the liquid form is paramagnetic. And molecular orbital theory is superior to both Vespel and valence bond theory due to 2 main factors. One factor is a paramagnetic nature of oxygen and boron, and second factor is a bond order and formation of the helium molecule, which is highly unstable, and show that there no bond is formed between the helium atoms. So due to these three factors, the molecular orbital theory is superior to both Vesper and Valence bond theory. And this, there is a bond order. Bond order is equal to bonding electrons 2 plus 2 plus 2 6, and anti-bonding 1 plus 1 2 divided by 2, 6 4. So there will be a 2. So that's why oxygen has a double covalent bond. Double covalent bond is there, and sigma bond and pi bonds are going to be formed. Sigma bonds and pi bonds are going to be formed here. Two bonds. Again, very strong and very stable bond is formed here because the amount of energy is 498 kilojoules. 498 kilojoules per mole amount of energy is required to break this bond, and also the 1.21 angstrom is a bond length. Higher the amount of energy, shorter the bond distance, bond length, stronger the bond. Not even the strongest one, very high, 900, more than 900 amount of energy is going to be required. So this is, students, structure, and we say the formation of oxygen molecule. This is a normal electronic configuration, 1s2, 2s2, 2p4. Here, two atoms of oxygen combine to give a molecule of oxygen. This is the one atom orbital, this is the second atom orbital. 4 electrons are in the p and 4 electrons are in the p. According to the rules, regulation, relative energies, you have to fill first sigma 2px. Sigma 2px, you have to first fill. 2 electrons will be accommodated here in bonding molecular orbital. Then pi 2py and pi 2pz, each 2 electrons, 4 will be here, total 6 electrons. And here are 4 and 4, 8. 2 will enter in the anti-bonding. So 1 will be in the pi star 2py and in the pi star 2pz according to Hund's rule. No electron will be entered in the sigma star 2px because all electrons weight are fused complete. 6 in bonding and 2 are anti-bonding, so bond order 6 minus 2 over 2, 4, 2 divided by 2 will get 2, so double covalent bond is formed. Bond energy is 498 kilojoules per mole, strong bond 1.21, the bond length. Electronic configuration 1s2 is complete K shell, sigma 2s2, sigma star 2s2, sigma 2px2, sigma, this one, pi 2py2 and pi 2pz2, and the last pi star 2py1 and pi star 2pz1 each. One electron, so it's paramagnetic nature. It is paramagnetic, it has toward magnetic field. This is the structure of oxygen molecule. Students, you have to be very careful and see very careful. That only 1 minute I am going to draw this up. Only 1 remains, that is a fluorine. Fluorine molecule. Atomic number is 9. 1s2, 2s2, 2px, 2py, 2pz. Now this one, 4, 3, 7, 8, 9. In the p there are 5 electrons. So So fluorine, 2 atoms to give a fluorine molecule, and electronic configuration is 1s2, 2s2, 2p5 like this one. Now, energy level diagram. This is the energy will be increased from bottom to top, and you have 5 electrons. This is the fluorine, atomic number 9, 2 electrons, and 1, 2p by this one, atomic orbital. 5 electrons here. The same. This is atomic number fluorine, which has atomic number 9. So 10 electrons you have to accommodate. So dear students, in the fluorine, again oxygen and fluorine, both, first you have to fill the sigma 2px. Oxygen and fluorine, 2px sigma. Sigma 2px. Bonding, molecular orbital, then pi bond. This is a pi, 2py, and this is pi, 2pz. Pi 2py and pi 2pz. So 5, 5, 10, 6 we accommodate here. So sigma is pi star, 2py, and pi star 2p z. This is sigma star 2px and p bonding molecular orbital. So 6 and 4, 10, no unpaired. If you see the structure, there is a no unpaired electron. All are paired. 5 and 5, 10. According to rules, oxygen and fluorine, if you see the relative energies of atomic orbitals, 6 sigma 2px first, then pi 2py, pi 2pz, 6 electrons in bonding molecular orbitals, then pi star 2py, pi star 2pz, again 4, 1 each, then 1 more, all are paired and bonding sigma star 2px's, and this is the energy diagram. So I am going to finish this electronic configuration. So students, K shell and K shell, they are going to be filled, then sigma 2s2, then sigma star 2s2, then sigma 2px through this lower energy, then higher energy, then pi 2py2 is equal to pi 2pz2, then pi star 2py2 is equal to pi star 2pz2, sigma star 2px is empty. This is the electronic configuration of the fluorine molecule. Sigma 2s2, sigma star 2s2, sigma 2px2, pi 2py2 is equal to pi 2pz2, then pi star 2py2, then pi star 2pz2, bond order 6 are in bonding, 4 will be bonding to where one bond. Fluorine has a one bond, and the amount of energy is 159. 159 kilojoules per mole. So dear students, here we finished all the structures, comparison of the valence bond theory and molecular orbital theory, similarities of they are going to form covalent bond both. These theories overlapping of atomic orbitals appropriate symmetry both the molecular axis. Electronic charge reside in the region between the atomic nuclei. Both formation of two types of bonds, sigma bond and pi bond. Both methods of atomic and molecular filled by according to the all same principles. Differences. Valence bond theory only involves the valence electrons, but molecular theory you can involve all electrons present in one, starting from 1s. Valence bond theory concerns the atoms do not lose their individual identity, but in MO theory, the two atomic objects lose their identities. BBT does not explain the paramagnetic behavior of oxygen, but MOT explains the paramagnetic behavior. BBT does not give the idea about the bond order, but MOT gives the idea about the bond order. BBT does not explain the existence of the helium molecule, that how it becomes hypothetical, but the MOT explains the non-existence of molecule according to the energy diagram. The students, we complete here all structures. Inshallah, next lecture I will explain the bond energy and bond enthalpy. These topics are now easy and approachable for you, and you have to see very well all these theories. Vesper theory, valence bond theory, molecular theory, very important. You have to explain very well. Thank you very much.